Welcome, guys. In this video, we are going to study related traits. In this type of problems, we are interested in finding rates of change of one variable in terms of other related variables. The major two steps that we are going to use when solving problems of this type is to find an equation that is going to relate all our variables of interest. And then we are going to take derivative from both sides, and then using chain rule, we are going to express our variable of interest in terms of other variables. All right, let's start then. So let's solve the following example here. Assume that oil spilled from a ruptured tanker spreads in a circular pattern whose radius increases at a constant rate of 2 feet per second. How fast is the area of the spill is increasing when the radius of the spill is 60 feet? So we have our oil tanker here, and the oil spills in the following circular fashion, and we can denote the radius of a spill as small r. So small r is the radius of the spill in feet after t seconds. T is the number of seconds passed from the time of the spill, and A is the area of the spill in square feet after t seconds. All right, then let's follow our two simple steps we have given here. The first one is to find an equation that is going to relate all our variables. So equation in this problem is quite simple. We are going to give an equation for the area of the spill, which is equal to pi r squared. Now we need to follow our second step. We need to take derivative from both sides. So taking derivative with respect to time from both sides will end up with dA over dt equal to pi, using chain rule here, pi multiplied by 2r multiplied by dr dt. All right, now we need to find how fast is the area of the spill is increasing with the radius of the spill is 60 feet. So we need to find the rate of change of area with respect to time. And we need to find this value here when radius of the spill is equal to 60 feet. All right, then we also know that radius increases at a constant rate of 2 feet per second. So dr over dt is equal to 2 feet per second. All right, then substituting our values here, we'll end up with rate of change of area with respect to time at the time when radius of the spill was equal to 60. So 120 pi multiplied by 2. So this is 240 pi square feet per second. All right, now let's move on to our next problem. Okay, next problem. So here we have a camera mounted at 3,000 feet from the base of a launching pad. If the rocket is rising vertically at 880 feet per second, when it is 4,000 feet above the launching pad, then let's denote some variables here. Let's call the distance of rocket from the launching pad as h. So this is vertical distance from launching pad to rocket. And we know that the rocket is rising vertically at 880 feet per second. So dh over dt when h was equal to 4,000 feet was equal to 880 feet per second. Then we need to find how fast must the camera elevation angle change? So here's an elevation angle. Let's give it a name. Let's call it theta. We need to find how fast theta should change at that instant to keep the camera aimed at the rocket. So by at that instant, we mean we need to find d theta over dt at the time when the rocket was 4,000 feet above the ground. All right, then if we follow our two simple steps that we defined before, first of all, we need to find an equation that is going to relate all our variables. Okay, now let's write down an equation for tangent of theta. Tangent of theta is then equal to h over 3,000. Now, taking derivative from both sides with respect to time, we'll end up with secant square theta d theta over dt is equal to 1 over 3,000 dh over dt. Now, we need to find d theta over dt at an instant when h was equal to 4,000, at an instant when h was equal to 4,000. Then this is 3,000, this is 4,000, and hypotenuse is then 5,000. When h was equal to 4,000, then theta was equal, well, in that particular case, we are interested in 1 over cosine of theta, and cosine of theta was equal to 3,000 or 5,000, so 3 over 5, or secant of theta was equal to 5 over 3. Okay, then d theta over dt at an instant when h was equal to 4,000 is then equal to 1 over secant squared, or simply cosine squared, and cosine is equal to 3 over 5, so 3 over 5 squared multiplied by 1 over 3,000 multiplied by dh over dt. Dh over dt at an instant when h was equal to 4,000 is equal to 880 multiplied by 880. Okay, and then calculating this value will find the rate of change of angle at that instant of time. All right, on to the next problem. All right, next problem. Suppose that liquid is to be cleared of sediment by allowing it to drain through a conical filter presented here that is 16 centimeters high. So the height here is given as 16 centimeters and has radius of 4 centimeters at the top. So radius given here. Suppose also that the liquid is forced out of the cone at a constant rate of 2 cubic centimeters per minute. All right, do you think that the depth of the liquid will decrease at a constant rate? Give a verbal argument that justifies your conclusion. So we know that liquid is pushed out at a constant rate, meaning that the rate of change of volume is constant. And if we take a look at the same amount of volume that water takes the instant when the water surface level is closer to the top of the filter is provided here. And if we denote this level as h, then the same amount of volume of water that water is going to take is going to be given as h at a later instant of time when the surface level of water is closer towards the end of the cone here. So we can see that this h is going to be bigger than this h at a different instant at an earlier instant of time. However, the water is pushed out at a constant rate, meaning that the same amount, those two amounts of volume should be drained out at the same time, at the same interval of time, suggesting us that when the surface level of water that is inside of our filter is closer towards the bottom of the filter, this H is going to drain out faster than the H at an earlier instant of time. So our answer to the first question is we do not think that the liquid will decrease at a constant rate. In fact, we will assume that the depth of liquid will drain out faster, closer towards the bottom of our filter cone. All right, next question. Find the formula that expresses the rate at which the depth of the liquid is changing in terms of the depth, and use that formula to determine whether your conclusion in part A is correct. All right, so let's follow our simple steps. Our first step is to write down an equation that relates our variables of interest. So let's start by writing down an equation for the volume of a cone. So V, it's the volume of liquid in the cone at time t, is equal to 1/3 pi r squared multiplied by y, where r is radius of the liquid surface at time t, so given here. Y is the depth of the liquid in the cone at time t. So y is the height of this surface level. Okay, now if we want to express dy over dt in terms of other variables, let's write down which values are known to us. We know that liquid is pushed out at a constant rate, so dv over dt is equal to -2 since the volume is decreasing. And that's pretty much it that we know regarding the variables that appear in our equation here. So our next step is going to be to get rid of r squared here. We'll try to express r in terms of other variables. So let's take a look at the following figure. So here in blue, I will draw our cone filter. And in red, we'll draw the level of water that is inside of our cone filter. So this is equal to y. This is equal to r. So we can see that these two right triangles, they share the same angle, meaning that the ratio of this height, which is equal to 16 over this radius at the top of the cone, which is equal to 4, should be equal the same as this height y over r here. So r is then equal to 1/4y. Now, if we substitute 1/4y instead of r here, we'll end up with the following equation. So v is equal to pi y cubed over 48. Okay, now taking derivatives from both sides and expressing dy over dt in terms of other variables, we'll end up with so dv over dt equal to 3 pi y squared dy over dt divided by 48. Now this is 16. All right, we also know that a rate of change of volume is constant and is equal to -2. So this is then -32 over pi y squared is equal to dy over dt. Now, if we ignore this minus sign for a second, then substituting smaller values of y is going to give us bigger numbers than, which is if we add our minus sign back, which is going to give us smaller negative number, meaning that the rate of change of depth of our water surface is going to decrease when y is smaller, or in other words, when this level is closer towards the bottom of our water filter. Okay, now let's answer the final question. At what rate is the depth of the liquid changing at the instant when the liquid in the cone is 8 centimeters deep? So we need to find dy over dt when y is equal to 8. So substituting this value here, we'll get dy over dt is equal to minus 32 over 64 pi. So this is minus 1 over 2 pi. So this is the rate of change of depth of our water inside of our filter. Okay, guys. Now this problem is going to conclude our section 3.4 on related rates. Thank you for watching.